Hi, everyone. Thanks for inviting me here. And I'm going to talk a little bit about remote sensing, a little bit about what my group does, and then also talk a little bit about drones and some ideas that I have, or maybe questions about maybe how library science can help my discipline of remote sensing, and maybe even save those questions or have those ideas as part of the discussion later. My talk's going to be, I'm going to give you an overview, a little bit about my research group. I'm going to talk a little bit about why we do what we do and how we've kind of become this unique special research group here at UNH. I'm going to do an overview of remote sensing. I mean, just a quick question, do people have a good idea or some modicum of an idea of what remote sensing means? Great, so I'll help define that. You guys probably all have remote sensing devices in your pockets or in your purses or in your bags. That's just basically the phone nowadays. And I'm going to talk a little bit about our work in the tropics to the tundra, and then I'm going to talk a little bit about the conclusions of our research. So I got into remote sensing partially because of this turtle. This is Flash. I got him when I was 5 years old. I got really involved in understanding geospatial or spatial things. So I moved from an apartment to a suburban woodlot, and I was fascinated by box turtles. I would collect them. I would paint with nail polish under their shell and let them go, record where I let them go, record where I found them. It was the beginning of a landscape ecologist and a nerdy little kid. Continuing along on those nerdy things is Dungeons and Dragons. I don't know if anyone here has played Dungeons and Dragons, but the concept of map building and world building and understanding where you are in this kind of cerebral fantasy world was quite a fun thing for me. So I'm part of the Earth System Research Center here at UNH. It is a soft money research institute, meaning that it survives on federal grants, state grants, and some foundation money. One of the original strengths was remote sensing. That's partially because Barry Rock here, who's going to speak later, was one of the original people here at Earth System Research Center. We do everything from measuring ice cores in Antarctica to Denali to doing work on indigenous sites across New Hampshire with an archaeologist that's associated with us, Megan Howie. And we have an expertise in GIS, and we also have some people that do more modeling. But really, ESRC is made up of about 30 PIs. We don't call them faculty, like a lot of other universities would call in departments, because as long as someone's bringing in money, we don't care what their educational background is. So we have some really great researchers that have masters, and they are treated as equal components of our group. We have people in the life sciences and biology and liberal arts associated with us. We have about 25 graduate students at a time. We bring in about $7 to $9 million per year in research funding. And this is just for about 30 people. We're part of a larger institute, Earth, Ocean, and Space, Earth, Wind, and Fire, if you want to call it that. And that brings in about, I think, about $100 million. So the Space Science Center brings in more money. So my research group consists of a few people. We're pretty small, but we mainly do these 5, actually, now I added one yesterday. I added snow. So we do 6 main avenues of research. Originally, I'm a forest ecologist. We do vegetation analysis. We're starting to work on snow with a researcher, Jennifer Jacobs, here for the Department of Defense. We do some Lyme disease or ecoepidemiology. We work with archaeologists in the Amazon and also Michigan and New Hampshire to look at archaeology with remote sensing. We work with human geographers, and then we also do some odds and ends, which I'll talk about if I have time. Our skill set tends to be remote sensing, which also includes all these other things, including statistics and modeling, a lot of computer coding. And about 6 years ago, we got into unpersoned aerial systems, or drones. We're trying to use the term unpersoned more than unmanned for various reasons, and I like it because it bothers people, and the people that are bothered should be bothered. So we have so these are the three main people that work with me: Christina Herrick, Jessica Del Greco, and Frankie Sullivan. Christina and Frankie are down in Massachusetts getting some of their sensors tuned up at a research place, Headwall down there. We basically kind of consider three things when we want to work on a project. Is it in a cool place? Not just temperature-wise. Are we working with cool people? And is it a cool topic or a topic that interests us? And it's really important to keep these three people kind of stimulated intellectually, because I want to keep them, because they know how to use these things now better than I do. So, and it gets us to some really cool places. So this is me. It's an awful picture. But that's a worm. That's not a snake. And this is in the middle of the Amazon, and it was amazing. So a lot of our funding comes from NASA. NASA has a portion of it, it's called Earth Science, and they fund environmental and earth science research. And they're one of the biggest funders of earth and environmental science. And they have this kind of statement on their website about why they want to do it. So they want to both know how to maintain the planet, as well as know about what life looks like in case they see it on another planet. And so with NASA comes satellites and Earth-observing satellites, and with that comes remote sensing. So what is remote sensing? I'll go through a few slides and talk about it. If people are really stumped about what I'm saying, or if I'm going too fast, raise your hand and interrupt me. We can treat this part of it like a lecture or as a discussion, but Barry Rock can't correct me. So, so really there's this amazing data source coming from the sun. It's the electromagnetic spectrum of things that are emitted or bouncing off objects. And remote sensing really is trying to look at those things without touching them. So basically, if you have your camera and you take a picture of something, you're doing remote sensing. And if we look across the spectrum from this cartoon, I don't know if people know this, XKCD, but basically you can see that we're really interested in the visible light as humans. We are, evolved primates. We're interested in seeing where the leaves and where the fruits are, and that's the spectrum that we look at. Some of the things slightly off of that are still used for remote sensing into the near infrared, and there's also some microwaves that are used to do remote sensing. I'm not that involved with that because it's complicated and it's way above my brain power. But you can also see that where the main Death Star laser is and how fast sound waves are. But really, the thing to remember is there's this frequency. Light has a frequency, same as sound in some ways. So the higher the frequency, the different color of the light that you could be seeing. And as remote sensors, we want the data immediately. So this is from the movie Prometheus. It's the Alien prequel. I'm a science fiction nerd. And basically, they throw this device down. It acts like a mapping thing, and it immediately brings it back to the program manager and tells them what they want to know. So as I mentioned, the electromagnetic spectrum includes radio waves, TV waves, down to the visible light. And that's really what we're going to focus on. Here's that slide redundantly, so I'm going to skip this. I do like that there's sinister Google projects, and we'll see if the computer crashes after I mention that. Now, we also mentioned remote sensing. A lot of NASA stuff is done using satellites and airborne platforms, but we do stuff that is remote sensing on the ground. So we sometimes stick cameras up on long poles to take pictures. Sometimes we fly them on drones on the bottom right, and some wire was in the way, blocking the beautiful picture that we were hoping to get. I'll talk a little bit about drones shortly, but this just kind of gives you an idea of remote sensing. And remote sensing, oh, it didn't change. Let me try again. Can also be things like this. These are lichens. These are on gravestones. And there was a researcher, Anne Pringle at Harvard a few years ago, and she was looking at the growth of these lichens to see she would know when the tombstones were put down, and she could estimate the rate of growth of lichens. It was a really interesting thing. And so what she was able to do was figure out what she wanted to look at, what the resolution or the size of the domain she was looking at. And this gets some things about why would we use remote sensing satellites. It's a great source of information that's available immediately. Some of the data goes back decades, and we'll talk a little bit about some of the data, how it's hard to get access to, but you as maybe librarians knowing about it could really blow the socks off of some researcher that didn't know about it. The great thing is there's all sorts of applications. So when our group learns one tool or how to use a hammer, we then go over and say, look at this hammer we have. Let's bang some other things together and see if we can find some new research problems. But there's a lot of problems with some of these remote sensing platforms. They're expensive. So this drone here with the sensor package is $120,000. And we can talk a little bit about, is that justified or is that a good use of that money? It's technically difficult. So these things are really hard to use. And you rely on some great researchers to work with on that. It's not always a direct measurement of what people are looking at. It's a proxy. It's a picture of this object, and lots of things are going on it. So if you're trying to understand kind of a process on a tree, like how much photosynthesis is that tree using, how do you look at that? You can look at how green the leaves are, when the leaves have been on, possibly how much moisture is on the leaves, and they're coming up with newer methods to pull that information out, remote sensing wise, but it is always a proxy. And then the biggest thing is clouds. So you have clouds that obscure things. You also have limitations in the area you can cover. So this drone can fly about 10 minutes to be comfortable. So that only covers about 12 acres. That's not a huge area if you're really trying to understand all of New Hampshire. And so we'll talk a little bit about some of these problems that our group has come across. And then resolution is a big thing. It depends on how close your camera is to the ground or how good your camera is, and that can dictate the resolution. So some of these satellites we'll see have really low resolution, and some have super high. So if we look at a high resolution, this is a satellite image. Does anyone know what this image is? It's the Taj Mahal. Did someone say that? So that's a pretty nice picture. So you can actually see quite amazing detail, but this image would probably be only collected once a year. And there's a lot of information that you might not need in that picture. You can do before and after. So does anyone know what this image is of? Can you guys see that okay, or? Okay. So it's New Orleans, exactly. So this is the Superdome before on the left and after. You can see a lot of the tiles or white stuff is blown off. You can see the flooded streets around it, and you can actually see a lot of humans around the area. So things like this can be quite vital for quickly doing emergency response. Some of them can be beautiful, like this volcano. You can catch wildfires. You can't see what's obscured by the smoke there, but you can see the fire burning. The different color here is a thing called false color composite, meaning that it uses the green, the red, and the near infrared shifted into the blue, green, and red for your computer. So really nice, healthy vegetation looks kind of bright pink. And so this is the Olympic Stadium for the Summer Olympics in Greece. And as you zoom in, you can see more and more. And you can actually see features that you normally can't see further out, like the lane lines. And so things that are linear features can often be determined more easily. So in New England, if we're looking at something like stone walls, those are things that sometimes pop out of some images. But these are really local images that are only covering a small area. This is South America, and this is collected by a satellite called MODIS. There's actually two satellites, Terra and Aqua, and they fly over really 2 times a day when it's daylight. They also fly over at night. But over time, over 8 days, they're able to get a cloud-free image of all of South America. Now, these are 500-meter pixels, so it would be about maybe the footprint of this library averaged. So all the colors in there are averaged for that resolution. So it's great for understanding vast vegetated areas. It's great for understanding arid regions maybe, but really to look at environmental response, you can't really determine too much about other things that are going on at higher resolution. So we talk as a remote sensor, we have this trade-off between spatial, like basically how big are your pixels, and then we also have this thing called radiometric. So the sensors are getting better and better. If we look at old satellites from the 1970s, this Landsat MSS, it only had values between 0 and 64. And now the newer versions have higher and higher numbers. So basically we can take that kind of color, the energy coming off the object it's looking at, and really kind of slice it up into nice little value. It's a little bit like listening to music. If you listen to video game music, it sounds kind of harsh. That's because they only have 256 different volume levels, while if you listen to a CD, you have, let's see, 24,000 different values for volume. So you can have this kind of nicer gradation of representing the real world. So here's an example of kind of a pixel size. You can see maybe a road and a house, and as you zoom in, that's what's represented as an individual cell in a raster image. And I'll just go through a real quick example. Our group works in Stordalen. It's a mire in northern Sweden. So it's right up there at the top. It's beautiful. It's the entrance to Lapland. There's reindeer all over the place. It's a wonderful place to work. Remember we were talking about MODIS. This is one image of MODIS taken in one day. It covers all of Sweden and most of Norway. When you zoom on into the area that we're interested in studying, this is what it looks like. So this looks a little Minecraftian. My kids love it. So what's going on there? Well, it looks like there's some sort of lake, and then there's some blue patches. If we use a higher resolution image, which you can't see at all, you might be able to see some more lakes. You can see a road. You can see a railroad. Still, if you zoom in a little more, you can actually see some of these lakes. So these things or features on the landscape were completely obscured with the coarser resolution. And as you zoom in, you can start to get towards seeing what the real landscape looks like, which looks like this. This is a research shack, which has computers that have robots that measure gas emissions from the mire or this permafrost region. You can see 2x4s, which the scientists have put as boardwalk across the landscape. And so these features would be even obscured in a high-resolution satellite image. So for example, here's a high-resolution satellite image. So there's that shack. And then this is what it looks like. Once again, not a great picture. There. So as a remote sensing, you're dealing with resolution sizes. Here's an example. You can have QuickBird or Iconos, which are about 60 centimeter resolution. You can move up to Landsat, and something like MODIS would be almost the whole football field. So one value for that whole football field. The other thing is to look at across the spectrum. So we talked about wavelengths. If we look at about 400, that tends to be blue. My students, I ask them what your favorite color is in nanometers, and most of them don't get it right. And you can see that the little bump there, right about 600, that tends to be where green is. So that's why vegetation looks green, because these plants, these different plant species, are reflecting green light off of themselves. And then as you get over past 700, you're going into the near infrared. But as a remote sensor, we can actually use these color differences to tease out and determine what the species of plants are that we're looking at. The other thing is temporal. Sure.
So how does the leaf color change over the course of the season affect when you do stuff like this?
That is a great question. So people follow the phenology across the whole thing. There's what? Okay. So how does the change of leaf on and off in color change how this kind of spectrum looks across time? People look at that specifically here in New England. There's a thing called PhenoCam, which has some cameras mounted on towers that constantly measure these changes in colors. And so it is an additional component of teasing out the species. Some species turn on their leaves earlier than others, and they also do change. We tend to try to do our measurements of something like this in one time period in August, when the leaves are fully on. However, that can really change from year to year. If you have a kind of drier summer, your leaves are going to have a different color as well. So that's a great question. So, and I'm not sure I answered it, but yeah.
Thank you. No, it sounded like, you try for the time of year when you've got the most consistency across.
Yep. And some people actually do multiple measurements and use that as a way to tease out the species too. Like, oh, look, this one didn't have much green at the beginning, and then it came on a little later. And I would actually, you can also look at plant diseases and how those things change for a species too. And I would defer to Barry Rockmore, because he teaches a course called Forest Health that looks at remote sensing to understand forests' kind of dynamics and health along those lines. Great question. The other thing we work with is the temporal resolution, and getting kind of at your question, is how frequently are images collected, and also what's the time scale going back in time. And so if we look at something like Landsat, it's going back to 1973 to the present. So we can look at the 8 different missions that have been launched. So you have Landsat 1, July 1972. Landsat 6 blew up at launch, so that was a little tragic. Landsat 7 has had some issues with its sensor, but people do still use it. So right now, it's really Landsat 7 and 8 that are up there with, I guess, Landsat 9 going up next year. So this is a continuous mission with different satellites put up. Satellites have different orbits. Some are geosynchronous, meaning they park at just the right distance from the planet, so they always stay at the same point over time, and they're over the equator, and it's basically the kind of centrifugal force versus the gravity that keeps them stationary. So a lot of weather satellites fall into that realm because they always want to be there. Other satellites that we use are polar orbiting, so they constantly go around the planet. And so as the planet is turning and they're going over, they image the whole planet over time. There's also active and passive. So if you look at your camera in your pocket or your phone, when you use the flash, it's active. It's sending some information or some energy out, and then you're recording what bounces off of that object. So that's a flash. It can be passive, where you just turn it on and it just takes a picture with the energy from the sun or the light sources in the room that are reflecting off that object. So there's a bunch of passive satellites. These are ones that often collect things in the visual domain or electromagnetic range. There's also some active ones, and I'll just mention these 2 things. This is about the end of the remote sensing, and then I'll talk about crazy projects we've had. But basically, there's LiDAR, which shoots a laser and measures how fast that comes back. It can tell you the distance, because we know how fast the speed of light travels. If you send out 300,000 of those per second, you can get a whole 3-dimensional aspect of the room. And so LiDAR is used in kind of autonomous vehicles or cars, and we use it a lot on one of our drones. And then the other one's radar. So radar actually shoots down microwaves and watches how they bounce off of objects, and that can tell you a lot about the features of the objects. So LiDAR basically shoots a laser, and then as it bounces back, you can tell things about the vegetation. There are lasers in space. So one of the biggest things there is this kind of glass system. There's a new one up, and it basically measures the height of things. Very useful for looking at the height of Antarctica ice sheets as well as Greenland. LiDAR can be used to look at individual tree crowns. So this is in Costa Rica. You can see individual tree crowns. You can see a little path through the woods there, so it's quite powerful. You can also shoot lasers from a kind of a R2-D2 robot, And the top is Harvard Forest, the bottom is La Selva, Costa Rica, and you can really see differences in the structure of the vegetation. So we use this to kind of look at what we're trying to understand. So if we're interested in looking at logging or crown or the individual species of trees, we might choose a specific satellite. This type of information you're using is really dictated by the question that you're trying to address. Megan Howie, an archaeologist here, she and I were developing how does this fit in with remote sensing? Kind of the same idea. You have your spatial scale of what your imagery can collect, your temporal scale about how often can it be repeated, and then the questions. And we kind of divided up archaeology into 3 types of questions. When they're looking at individual sites, they're kind of try to find the sites. Intersite, they're trying to look at how those sites are connected. And the really kind of what's not done by most archaeologists is the landscape processes. What is the landscape like and how is it functioning compared to the surrounding, and how are humans keying in on certain components of that landscape? And so as we start to try to think of new ways to fly with drones, we often realize that we're repeating what was done in the past. And so we can talk about early remote sensing here. The first remote sensing was done by balloons and birds. And these are just fun to look at, pigeons with cameras. The first aerial photograph was of a street in Paris. You can see a little liaison down there, or maybe someone just getting their shoe shine down there in the bottom. They were put up on kites. So the first aerial photograph was taken over France on a kite. We can look at the devastating fire in San Francisco, and this guy put a camera up on a kite and took some pretty drastic and impressive photographs. There's other reasons why people were taking photographs. So this is one of the first recon satellites developed by the US government. So that's a picture of it. These missions were flown from early 60s until the late 60s. They were called Corona. These satellites have now been declassified. And so if you are working with a researcher or archaeologist that's looking at parts of the planet that wants to know what it was like in the 60s, often these areas are covered. What's really fun is to think about how this worked. When you explain digital cameras and analog film as the opposite to students, sometimes they don't know about that. So the Corona satellite would actually eject its analog film canister. It would float down on a parachute, and then a plane would have to catch it. And then they would take it back and develop the film. And so it is just phenomenal to think that that was kind of the cutting edge technology. So as we've advanced so much, it was just so precarious now, or then. So my kids like some of the high-tech planes. So this was I forget which one. Do you remember which plane this was? Blackbird. Okay. And so these things were alien. I mean, they leaked fuel when they were on the ground until they got up at speed, because things got so heated up that they expanded, and then it stopped the fuel from leaking. The people that flew these lived in their own kind of town in California and had their own family interactions. Like one had to do an emergency landing in Sweden, and they warned the people when it landed, and people freaked out because it looked like an alien vehicle. But it was used for basically during the Cold War era, taking images of the ground. Another one you might have heard of is U-2, not the band, but there was a plane, the U-2 spy plane. NASA's converted an older one into a remote sensing device, and it carries this really high-resolution camera called Avarice, and so now we're using U-2 planes for the good of environmental science. And that data is often available in some areas. Now my work, if we jump into the tropics, focuses on Amazonia. It's a huge river, 11 times larger than the Mississippi, huge amount of species. My friend's wife is a fish biologist. She goes to the fish market and buys fish and then genetically tests them instead of going out and collecting fish in the field. So it shows you how diverse their markets are too. It's really important for global carbon and water cycling. Once again, immense biodiversity. And then you also have the Cerrado, which is the savanna-like area to the south of the Amazon, which also has a lot of endemic or species that are only found there. Amazon has about 30% of all the plant species. On average, one new primate species is found per year, which I find is amazing. These are some of the animals I've seen. Actually, that's a howler monkey from Costa Rica. And that's a grub from my backyard in New Hampshire. But that's a jaguar footprint. And the Amazon's drastically changing. We hear about this often, but it's being converted. So the bottom left is a fire project that NASA had where they lit the forest on fire, and it created such an amazing plume of smoke that they created what they call pyrocumulus, a fire rain cloud with lightning in it. But a lot of this land is being converted for pasture and also logging. My group works mainly in the tropics, and the reason of the interest in the tropics is the permafrost collapse, the thawing of this kind of northern peatland, and the changes in how that has on the carbon cycles up there. And so there's a huge amount of area that has soil content there in the peat, and it's collapsing a lot. And as it collapses, it changes into anaerobic, so no oxygen as the decomposition, and it creates methane, which is also a greenhouse gas. I got involved in working in the tundra with Ruth Varner. She's a researcher here, a biogeochemist. My hobby is sound. I like to record sound, and I had these underwater microphones for my kids. We were going to go to the Caribbean and try to record mantis shrimps and dolphins or something like that. And Ruth said, do you think you could hear little bubbles? And so we created this really cool device. These are little microphones put underwater. And basically we're trying to get at one component of this, which that turns it off. There we go. Basically there's three pathways for methane. It can oxidize or diffuse out of the area. It can go up the parts of plants, or it can create little bubbles and pop up. And people didn't really know where the bubbles, how many there were. And we created these little audio devices that recorded MP3s, and it's been pretty fun. Another thing we do in the tropics is we look at forest structure. And I'll go through this talk. Actually, how am I doing for time? Maybe we should jump right to the drone stuff. Okay, great. So we'll keep going a little bit. Actually, we're going to skip the forest. Actually, we'll talk a little bit. I'm all over the place. Algorithms. So an algorithm is basically a flow chart. And so as we have this remote sensing data, we like to figure out the steps to find something meaningful from it. And an algorithm is nothing more than a flow chart. So let's think about if you're driving your car. How do you change lane? What's the first thing? You're driving your car, what am I going to do? Look, okay, that's good. So I look at, that's good. So none of you are from Massachusetts then, huh? Okay, so you look, and then what do I do? Blinker, okay, so I'm going to turn to the right. Look, boy, you guys are, the students never look twice. They just, okay. So then you turn the wheel. And then straighten. So that's the other thing, is that students often forget to straighten. But that's a series of steps. I mean, you can look at it as a flow chart on whether you're going to drive or walk to school. And these can be how you process in computer code these remote sensing images. I also like to look at it as a series of solving Rubik's Cubes. I cannot do a Rubik's Cube, but if you mention that to some students, they instantly understand what an algorithm is. As far as our liberal arts background, does anyone know who this person is? That's good. What? Close. Well, so this is John Cage. So John Cage is a composer. I love him because he's the most disruptive composer that I know of, and he wrote a lot of things about algorithmic composition. So he basically flipped coins or used the I Ching to determine how he was gonna. So a lot of times I talk about music and how you can create music using algorithms for the students. This is my favorite musical band. It's a band called Autiker, and their albums are purely computer code. So they write computer code and generate sound, and it is phenomenal. It's not going to change you emotionally, but it is magic for your ears. It is a kind of like the heroin of sound. Can you continue to try to chase that down? So our group does a lot of things with automated algorithms or crown delineation. So we basically try to look at high-resolution imagery of trees and determine the edges of these crowns. And so it really looks at a little bit like when you look at apples in a supermarket. You look at the apples, you see some bright areas, and then you see the valleys between the apples that are darker. And so we do the same thing where we find the local maximums or the global maximums, and then we also find the pits or the in-between valleys between an image. So what happens is we actually send these transects out from a center point, which we've determined is the top of the tree, and then on the bottom right there, it can kind of define where the edges of the trees are. So it's a really simple algorithm. We've used it in about 8 papers now, and I'll just show you a real quick example here. So this is a LiDAR canopy height model of an area in Brazil, Tapajós National Forest. You can see individual palm trees there. And so having someone try to determine how many trees and the size of the trees, it can be daunting. We have done that with an undergraduate, and it took them 2.5 weeks. We call it the crayon method. They sit there and delineate the individual crowns. We've done this on areas, 40,000 times this area. So 40,000 times 2 weeks, that would be many graduate students, or many undergraduates too. But we can do it almost instantly with this crown delineation that counts the trees. It's really fun and it works pretty well. Sometimes it fails, sometimes it lumps trees together, splits them out. An example of it being used is in looking at logging. So here's an area in Brazil. You can see that areas that are unlogged, they're logging concessions, they have more larger green trees as we depicted them. And you see more small trees where areas have been logged, and you can see the year that they were logged. So that's one of the things that we use with that crown delineation. We also do a lot with kind of terrestrial LiDAR, where we put something down in the forest and we run away, or we put on eye protection, and then we try to determine what the structure of that forest is, or the architecture of the forest. And so we've been doing that for a little while in Costa Rica and Harvard Forest. I'm going to skip over the next. I want to talk about all this, but we'll skip over this and we'll talk about something more fun. So space archaeology, we've been doing work in the Amazon. So when people talk about space archaeology, they are not talking about the faces on Mars that people see. They are not also talking about old junk up there that we've left. It's basically a series of projects that NASA has funded to try to understand and tease out archaeological information using satellite imagery. So our work tended to work on how many people lived in the Amazon. So if people have read the book 1491, what was life like before human contact here in the New World? In the Amazon, there's just a lack of evidence. It's an old seabed with a forest grown on it. There's very little stone. Things decay really quickly there. It's hot, humid. So people really don't have a good key on how many people live there. Some people say no one lived there. Some people say millions of people live there. And one of the few ways to get at this is a thing called terra preta, or Amazonian black earth. And it's basically like a thing called biochar. It's this charred, composted soil. It's really black. It's nutrient rich, and it has really kind of different dynamics in holding water and nutrient dynamics. And so we coupled with Eduardo Neves, who's a Brazilian archaeologist, to start to find these sites. The idea was kind of we would look at the tree species possibly, kind of that same thing. This is New Hampshire trees. And we were going to try to tease out maybe the plant species or use these differences to determine where these sites are. So we're going to use this thing called hyperspectral. So remember, your camera has red, blue, and green. Hyperspectral divides it up, instead of just 3 colors, basically into 240 or 270 different colors. And you can tease out little information such as these plants, individual plants. So we were going to use this satellite called Hyperion, which was an experimental satellite by NASA. It was really cool because we got to tell the satellite where to take pictures. Some satellites constantly take pictures. They're the coarser ones. Some you have to say, you get in there and you say, could you please take a picture? And so we would be lowest people on the totem pole. First it was probably special ops, then it was people looking at landslides and catastrophes, and rightly so, and then we were at the bottom. And so we would fly over, we could tell where it was flying at any point, and then it would take a picture, and then it would tweet us. And it would say, hey, I took a picture. Why don't you look at the picture and see if it's what you wanted? And if it is, then we'll download it from the satellite. And if not, they would delete it right from the kind of cache on board, so they wouldn't waste the time downloading unneeded data. It was really cloudy or whatever. This was a much better use of Twitter than, what many people are using Twitter for. And this is what it looked like. It was actually these really long strips. So if we were interested in just one area, that's about 7 kilometers wide and about 140 kilometers long. And so, to our chagrin, if you looked at where the Terra sites are, which are blue, along the rivers running west to east, and then the satellite that kind of connects across it, we were often missing our sites. So those are the ones that we tasked, and we only got a few. So this is a little bit of our own embarrassment. So we continue to try a different satellite. So here we are in Brazil. Those are the Terra sites that we went through records. We went through record after record of trying to look through old books to find out where people had determined where these Terra sites are. We ranked them on how sure we were based on the person that recorded that information. We mapped them geospatially across the landscape. So this is a nice kind of elevation model, and that's where the Terra sites were. We started to use satellite imagery across the whole Amazon. So remember, we talked about MODIS. And we used a really cool modeling technique called maximum entropy. I won't get into that, but we were able to predict where we think these Terra sites were across all the Amazon. And it's more complex than what people have said. There were a lot of people in some areas, and then some areas didn't have that many people. So these are the stories that don't get on New York Times. The New York Times says, there's nobody there, or there's tons of people. And when you say things are a little more dynamic or complex, sometimes that doesn't hit the front pages. But it was a really good study, and NASA was quite happy with our findings. So I'm gonna skip through a few other slides here and go right to drones, okay? And now we'll get, so you should have gotten protective eye gear in your packet, as well as a small helmet, because we're going to fly this around. Our group has a few drones. We have smaller UASs, like this one here. This one's about $300. We bought this when one of our drones was delayed in shipping. And this thing works great, especially for demonstrations. It sets up a little wireless component. You can then get the program on your phone. You can have 20 students all looking at the image at the same time on their phones of what this is flying around. If this crashes, we're not upset. This doesn't put up red flags when we're flying it somewhere. At a university, you are a commercial entity. Even if you're considered nonprofit, you're still making money from flying drones, if you're flying drones. So you need a special license. And so you have to get a thing called a 107 license. It's a test. And so in our group, we have 2 people that have those licenses that fly the drones. There's a lot of different cameras that we put on there. We have normal cameras that you can buy at Best Buy. We have, this is kind of that near-infrared red and green camera. This one is broken because a student tried to plug in a power supply into the GPS and fried the board. And my mom, as a teacher, said, that I didn't teach the student well enough, and I should be it was a good learning experience for me, and she's kind of right. It is my fault. We have also LiDAR on these drones. That's a newer thing. So this is a LiDAR sensor here, and we have a hyperspectral sensor here. Now, normally these sit on a gimbal underneath the drone, and they're balanced and they level out. Frankie and Christina, once again, have taken those down for a tune-up, so I didn't have those today. But we can talk about a little bit about drones. We have big drones and little drones. This is an 8-rotor. I can lift about 50 pounds for a short amount of time. But normally our cameras are only about between 8 and 12 pounds. This drone, when fully loaded with batteries and cameras, is under 55 pounds. That is the cutoff before you go into the next step of drone use. And so keeping it between half a pound and 55 pounds is really the goal. We have different drones. So we have this hyperspectral drone. This is a DJI Matrix 600. It has a hyperspectral camera. We've flown it to study tree species at Harvard Forest and Bartlett Forest in New Hampshire. We've flown over lakes at Lake Sunapee. This summer we'll be flying over Lake Auburn, some of the Belgrade lakes, and Lake China in Maine to look at cyanobacterial blooms, to really look at these weird algal blooms. And we've also done archaeological sites for Megan Howie out at Durham Point Road. That is within the Pease Air Force space, so we have to actually get permission to fly there. So we notify the tower, and they divert these huge tankers that are coming into Pease. It is amazing because you have your little drone up there, and these big planes just fly right around the area you told them you're going to fly. And as soon as that window is over, they fly right over you. And so we are really, really careful about following all the rules for our drones. I'll continue to talk a little bit more about our drone work. These are some of the cameras. The other thing that's really important is we have a really high GPS and an IMU, which is basically an inertial motion unit. And that allows us not to have to kind of figure out where points are on the ground. It automatically will do it with the software as the drone. So as the image is being collected, it's embedding information along the way. This is Frankie setting up the drone to fly off of a boathouse at Lake Sunapee. That's Kathy Weathers and Midge, who owns the property. This is this drone up here. So this is our heavy lifter. One of the ones we really like is one that's made out of styrofoam. So this is a company in Texas named Robata. They take $300 kind of kits, and then they convert it and put a little robot computer in there, and then charge us $4,000 for it. But it works so well, and it flies. It's hand launched. So there it's hand launched. Here we are in Oregon flying it. When it crashes, you can just find tape or decals at the local truck store and tape it up, and then fly it again. And it is a workhorse. So we were working with a lot of landowners that do ranching and forestry in eastern Oregon, kind of the same area where they took over that reserve, if people remember, a few years ago. So we were told we would do town hall meetings, and people would bring sidearms to the meetings, and we were told to take out earrings and cover tattoos if you're male. It was interesting. But the landowners were really open for these new ideas. They were farmers. They were interested in how to utilize kind of drones for the research. And so you can see that we would fly this over their area. We would do a thing called structure from motion to kind of get a three-dimensional view. If you remember those old slides that you would look at that would have 3 dimensions just from stereoscope. Same concept, but with 700 pictures. We could get kind of a topography of the trees, and then you run that stupid algorithm that I was talking about that I invented, even on that, and it worked. So we've been doing that in Eastern Oregon. We're also really into educating the public or working with the public. Educating the public sounded a little a little lofty here as an academic, I'm sorry. But we really want to explain why we're using drones for research. And as soon as you start to explain it, people have new ideas on how to use them. And it's really fun to discuss with these landowners. Here's some hyperspectral imagery, not showing up very well, of Lake Sunapee. So we're trying to look at the cyanobacteria. Another way to look at cyanobacteria is to look at temperature of lakes. So Christina, who works with us, has been looking over the past 20 years about what's the temperature of lakes across. And so that Landsat satellite has a thermal sensor, so it can tell the temperature coming off of the surface of the land. And so we've been able to try to tie the temperature of lakes, which is on the bottom, that's measured, and on the right side of these graphs is the estimated temperature from the satellite. So she's been doing a great job on that. One of the things with drones is you need to really have a good plan of where you're going to fly. So these are our flight plans using a software called UGCS, Universal Ground Control Software. We use it for all our different drones, so our drones can use all the same. It's kind of making sure we're consistent with what we're doing. We store our flight paths so we can actually repeat them no problem. We can share them with other researchers if they want to do the same. And that could be an important thing to conserve as far as research, maybe in some sort of documentation. We have a really important data flow of how we process our data. We have a lot of data coming through, so one flight, one day of flights with this creates over 50 gigabytes of data, which starts to really test some data storage for us. We also really interested in sensor maintenance and the flight logs. So what comes off of, not only hyperspectral, but is the three-dimensional aspect of the forest. So if we look at the top, you can see the red are the top of trees. You can see kind of two fields, and then you can see on the right more trees, and then actually the lower area of a river. What's great about LiDAR is you can then actually use some software to remove the trees and determine what the topography is like underneath that. And so you can start to get at what's under the canopy. You can find old stone walls or cellar holes. We've actually found old cache pits working with Megan Howie in Michigan. So wrapping up a little bit about the tundra. We're part of Ruth Varner's projects. She's been working in the tundra for a number of years. We've expanded her work with her into Alaska and northern Canada. So now Frankie gets to carry bear spray as well as flying drones up there. I tend to go to Sweden because it's a nice cushy lodge for me. But here's Ruth Varner. She's a really active person. We have an REU program that we basically she's been running there for 3 or 4 years. And we've used that as a great avenue to kind of see what grad students actually function well in the field, and then try to invite them to UNH to continue their studies as a graduate student. Sophie Burke in the center there, top right, has won a number of awards recently here at UNH. Last summer, Sophie and Christina and I were in Finland. It was 95 to 98 degrees. It was so buggy, it was buggier than the Amazon. It was brutal. And in Sweden nearby, there were forest fires that they had never had before, and about 8 European countries actually donated forest fire fighting equipment to Sweden to deal with this. So there is some definite change that's going on with the climate around these areas. We've been flying that's the little cheap fixed wing, $6,000, but it's awesome. You can see the back, it's already been taped up this year, and so this is Ruth Varner's son. This is my grad student, Jessica Del Greco, and we've been flying there for about 6 years. So you get these wonderful images of the landscape. So that's the Swedish research shack. It looks like something out of IKEA, or I don't know if you can see that, but we're right there flying it. I'm standing on the boardwalk there. Dan Fennel is a student who's actually helping me fly. We take about 700 images. We stitch them together using some software, It determines where they are in three-dimensional space. So you can see that the wind was blowing kind of straight up. So when the plane would fly, it would get off course, and then it would have to correct and re-fly where it wanted to. With this drone, we don't have a really high GPS or IMU unit on it, so we actually have to do this thing called georectification, which basically is tying some picture that's in imaginary world to the ground. And the way I like to explain this to students is to imagine Pinkie Pie and that's Ryan Gosling, right? And imagine if you mapped his features onto Pinkie Pie. What would he look like? And that just blows people's mind. But basically, you take where is his nose relative to Pinkie Pie's nose, chin to chin, has a smaller chin, it appears. Forehead's a little different. And so the students get images like this. And it's a really interesting way to show how you can warp an image as well as the need for really good measurements on the ground. So we've been collecting images over this mire. So this is about 2 kilometers by maybe half a kilometer. So 2014 to 2018, we do a thing called neural network, fancy math classification of these different vegetation types. And we look at how it's changed over time. And there's Jessica collecting the really good GPS points that we need to collect. So the same time, maybe 2 years before, and she's in winter outfits up there. So things are quite variable. So 2014, 2015, you can see some of this wetlands and this permafrost collapse. It turns into a wetland. More wetlands specifically up here. And then it's really getting wet. And we don't have 2018. We've also been flying this little drone here every 3 days, and we're having students fly those. And basically, they're looking at how these thaw ponds expand and contract. And that's the American shack, which is basically an old trailer that they just dragged out there. Not as cool as the Swedish IKEA version thing. I'm just going to go through some odds and ends of what our group does and some odder things that might be of interest to library scientists, and then wrap it up with kind of how we've interacted with the library, which is really great here at UNH. We've been working with a historian to try to document sites that are being lost in Mosul. So we basically have used an app or a thing called Art Collector on people's phones, and people can take pictures, punch in information, and it automatically is sent to our database, and it can be displayed on a map to figure out where things are being lost. And you can take different data sources together. We've become very apt at understanding how GPS points are. So at one time, the handheld ones that you even have in your phone were great, but as our drones have gotten, measuring centimeter level images, we need to know a little more about where we are on the planet, and that's included us learning about GPS a little better. We've also worked with area teachers. This is a thing through Project SMART. Rich Levergood is a physics teacher at somewhere in, Northwood, whatever high school's there. He helped work with students to build these kind of basically spectrometers. They basically measure the light levels of red, blue, green, and other. We put these up on a drone, and the students were able to measure, try to do cyanobacteria or different vegetation types. Throughout this whole thing, I've talked about drones as being a disruptive technology, but there's still satellites that are being put up there. So this is NASA's, what they call their constellation for Earth science. So we have things like Landsat, MODIS, Landsat 8, and a few other ones up here. And these are things that are really important for Earth science as well. And some of them are out there. And I want to talk about one of them or two of them. GRACE measures the gravity on the planet. It doesn't take pictures of the Earth. It's still a remote sensing device because it's remotely sensing the planet. What it does is it has 2 satellites that fly along, and it constantly measures the distance between the 2. And when one goes over a higher gravity area, it gets pulled further away than from the other one. And so it measures this distance, and it can actually determine the annual fluctuation of water in the Amazon. It can detect the depletion of the aquifers in India. It is a really, really cool. We're trying to use it to understand the beginnings of volcanic activity in the Aleutian Islands with Julie Bryce and her grad student here. It's a really cool satellite. Another one's EcoStress. So there's the International Space Station. They sometimes put remote sensing products that are kind of experimental on the side of that. So EcoStress is measuring basically the temperature of plants across the planet. And so we have a proposal in to try to look at the temperature of lakes using this sensor. What's cool about that is it measures at different times of day instead of 10 o'clock every day like Landsat. Another one is, this is them being goofy, but there's a thing called JEDI, G for genius, not J. And basically, this is a laser on the International Space Station that shoots down and tries to measure the vegetation across the planet. So that's pretty cool. There are these things called the A-trains, so satellites go over right one after another. So first you have Aqua here, then you have CloudSat, Calypso, that's Aurora. And so you have these satellites that are following one after another. Sometimes you can see them from the ground. Over the next 15 years, there's going to be a huge amount. So we have 30 space agencies that are launching Earth-observing satellites. There's going to be 285 new missions, hundreds and hundreds of sensors, some of them new, some of them different, some of them repeating. And these are going to be great sources of information that either students and actually other researchers might not know about. So it's not hard to actually have a list of these and sound really smart. Like, I memorize a few of these, I go into a meeting and I'm like, well, what about blah, blah, blah? And then it sounds like I'm on the pulse of NASA, which I'm not. Because once again, I'm always just fake it till you make it. So as far as library science, how we interacted with librarians, one of the things is trying to find old aerial photos. We were working on a project in Brazil, and we understood that the US Navy had collected aerial photographs across all of Brazil when there was a regime change or a dictator was put into power there in the 60s. And so we've tried to really utilize that and work with librarians to try to find those. Actually, more librarians in Brazil. We work with librarians here to help us with our metadata. So we often work on a proposal. We have to have a good metadata plan. We write what best we can, thanks, as researchers, and then we send it to Patricia, and she tells us, oh, this is good. She's nicely congratulatory. But also, why don't you reword this, and I suggest you change this, and I don't know what you mean here. Old maps are another thing. So we remember Pinkie Pie and Ryan Gosling. Old maps can be georeferenced in the same way into a GIS or remote sensing, and so we've been working with some researchers to do that for them, and then use that with current satellite imagery. At UNH, we also have a GIS librarian or science librarian, and Hannah's very involved with helping students. So when I teach my GIS course, it's always interesting when they go and get help at the library, thank goodness. We're also interested in data storage. In the past, it was good enough to just say, oh, we're going to put it on a website and we're going to be able to have it accessible to people. But NASA and NSF is wanting a more definitive and long-term plan for data dissemination. Multimedia. We have a multimedia group here in the library. I don't know if they're actually part of the library, but we've used them to collect images, take microphones to the field to really up our social media game. Now, I'm not good at social media, but some of the students that we work with are really good, and we let them go with some of the images we collect. We've been getting involved in the DOI. What's that? Digital Object Identification. What is it? Yeah. And so for us, papers are gold stars that we get as researchers, but really the data could be a gold star too. I mean, if that's what people are accessing and that's what they're interested in more than my algorithm that I've created, then that's really a helpful way to kind of get recognition, as well as how the library helps us. And one of those is understanding Creative Commons. How do we feel about sharing the data? Do we need to be notified? And understanding and navigating what's considered Creative Commons is important. And then the other thing is knowing what's going on in campus. UNH is a fairly small kind of university. I know that's maybe you guys come from larger universities, but often one department doesn't know what the other's doing. And there's also like small fiefdom fights and all that, but we won't get into that. But knowing who's doing what can often be an integrating feature. We've relied on the library sometimes to tell us what other people are doing. So that's been a useful thing. I really think that data storage and helping us with DOIs is a really, really important aspect. So that's about it for the talk. I really appreciate your time.